Welcome to this explainer. If you're looking to truly master data structures, you've absolutely found the right place. Today, we're going to build a rock-solid understanding of how to traverse linked lists in C. We're talking looking under the hood at memory, walking through the logic step by step, and figuring out how to do all of this without getting lost or, worse, crashing our programs. Let's get into it. This is all about understanding and traversing nodes. Okay, so take a look at the basic structure of a linked list. We've got a chain of 3 connected blocks here. Each block is a node, and it contains 2 really critical pieces of information. First, you have the data. That's the actual value we care about. Second, there's a next pointer. Think of this pointer as a bridge linking directly to the very next block in memory. The first node points to the second to the third. But check out that final node. Its next pointer just cleanly points to null. In C, null acts as a total dead end. It's the definitive signal that our list is finished. Which brings us to our critical baseline concept, traversal. What does that actually mean? Well, traversal literally means visiting every single node in a linked list sequentially, one by one, from the beginning until there's absolutely no one left to visit. You start at the head and you just walk the chain until you hit that null pointer. I actually really like to think of traversal using a conga line analogy. Just imagine a line of people holding on to the person in front of them. Person 1 is at the front, they're the head. Person 1 holds on to person 2, who holds on to person 3, all the way down to person 4, who, well, isn't holding on to anyone at all. They're the end, the null. When we walk this conga line in C, we usually want to accomplish one of 2 main tasks. Task 1 is counting nodes, so keeping a running tally of exactly how many there are, and task 2 is printing data, where we actually display the specific values stored inside each node along the way. Let's dive into task 1, counting the exact number of nodes. Here's a fairly simple C function called countNodes. We start off by setting an integer count to 0, and we create a temporary pointer called PTR that starts right at the head. Then we enter our while loop, which keeps running as long as PTR is not equal to null. Inside that loop, we bump up our count. But here is the real secret sauce, the pointer jump. Look at the line PTR equals PTR-next. This line is everything. It literally tells the pointer to stop looking at the current node and jump to whatever node the current one happens to be pointing to. This repeatedly advances our pointer through the list until it finally lands on null, which breaks the loop. Now, seeing the code is one thing, right? But to really master C, you kind of have to think like a compiler. When that loop is actually running and that pointer is doing its jump, what exactly is happening block by block in the computer's memory to make that counter tick upward? To figure that out, let's just step through the debugger watch table exactly like the computer executes it. Right at the start, our count is 0, and our pointer PTR is hanging out at memory address 1000, pointing to node 1, which holds the value 45. In step 1, the computer asks, is PTR null? Nope. So it increments the count to 1, and the pointer jumps to PTR.next, which happens to be address 2000. That's node 2 holding 98. In step 2, is PTR null? Still no. Count bumps to 2, the pointer jumps to address 3000, which is node 3, holding the value 3. Step 3, is PTR null? No. Count becomes 3. But now the pointer jumps to the next of node 3, which is null. So finally in step 4, the loop condition asks, is PTR not null? Actually, it is null. The condition evaluates to false, the loop safely exits, and we're left with our final result, a count of 3. Let's zoom out and look at the complete C program from start to finish. Down in our main function, we first create our list. A node with 45, pointing to 98, pointing to 3, which then points to null. Next, we call our countNodes function, passing in the head, and we store that result in total. We then print the output, which proudly says number of nodes 3. But definitely don't miss lines 22 through 28 here. This is a vital trailing loop used to free the memory. Just like we traverse to count, we set a current pointer to head, make a temporary copy of the current node, advance the current pointer, and then free that temp memory. It's so important to do this so we leave no memory leaks behind. All right, let's move on to our second main traversal task, printing the data inside every node. If you look at the print data function, do you notice something new right at the top? It's an empty list check. This is incredibly important. If the list is entirely empty, we just print linked list is empty and return early. If it's not empty, we spin up our while loop just like before, but instead of counting, we use printf to securely print our data out before we advance the pointer. It is actually fascinating to track the console output line by line as the pointer evaluates the list here. At step 1, the pointer evaluates node 1 and prints its data, 45. Then it advances. At step 2, it evaluates node 2, printing 98, appending it right to the output to make 4598. At step 3, it evaluates node 3, printing 3, making our final output 4598.3. Finally, the pointer hits null, safely exits the loop, and we are left with a perfectly printed sequence. Putting this printing logic into a complete C program really lets us contrast two wildly different scenarios. First, we've got the normal list test. We create our 4598.3 list, pass the head to print data, and it gracefully outputs 4598.3 null. Perfect. But look just below that at the empty list edge case. Here, we create a node pointer called empty and set it right to null. When we pass this empty list into our print function, our early check safely catches that null. It skips the traversal entirely and just gracefully prints linked list is empty, all without crashing the system. This is all about preserving data and preventing crashes. Now, you might have noticed that in literally every function so far, we never actually use the head pointer to run our while loops. We always make a temporary variable like PTR or current. Why do we do that? Well, because the head pointer is essentially the only tether tying your program to your data in memory. If you lose the head, you completely lose the entire list. Making a temporary copy allows you to safely walk through the list while the original head stays securely anchored at the front. Let's contrast these two methods directly, because it's a big deal. In the safe approach, method 1, we create a temporary pointer PTR and set it equal to head. We traverse using PTR, the original head is perfectly preserved, the list is safe, and hey, we can traverse it again later. But method 2, highly dangerous. Inside the loop, it executes head equals head.next. By doing this, you are physically moving the head anchor down the line. Once that loop finishes, head is null. Your original starting address is completely lost. You can't traverse it again, and that memory is just stranded. Honestly, never do this. And this brilliantly illustrates exactly what happens when we skip our safety checks. If you have an empty list where your pointer is null, and you try to ask the computer to read the data inside that null pointer, the computer absolutely panics. Attempting to access empty.data triggers a catastrophic segmentation fault, which crashes the application instantly. But the good news? This is entirely prevented by the safe pattern. Our early exit condition guarantees we never try to extract data from thin air. So, let's synthesize both tasks and our safety rules by reviewing this complete master program. Over in main, we successfully create a list, 10 pointing to 20 pointing to 30. We then call printListHead, which safely traverses using a temporary variable and correctly outputs list 10, 20, 30 null. And on the very next line, because we preserved that original head pointer, we can safely traverse it all over again, calling countNodes head to output count 3. Finally, we reliably free the memory using our dedicated while loop. This is a perfectly safe, fully functional application. Before we wrap up our rules, there is one special case of traversal you really need to know about: appending a new node. Let's say we want to add the node 30 to the very end of a list holding 10 and 20. We can't actually traverse all the way to null in this case. If we hit null, we've gone too far, right? We'd have absolutely nothing to attach the new node to. We have to traverse to the last node. The secret logic here is while current.next is not null, that subtle shift means the loop stops exactly on the node holding 20, simply because its next points to null. Once we're stopped on 20, we just point its next to our brand new node 30, and boom, we've successfully established the new link. Finally, synthesizing the master template. It is time to synthesize everything we've talked about into an unbreakable 4-line template. Honestly, just memorize this structure. Line 1. Initialize your temporary pointer. Struct node current equals head. Line 2. The safety net. If current equals null, return. Line 3. The engine. While current does not equal null. And line 4. After processing your data, reliably advance the pointer with current equals current to next. This little shell right here will get you safely through almost any linked list scenario you encounter. To really cement this, try to treat these 4 rules as an absolute pre-flight checklist every single time you sit down to write code. Rule 1. Always use a temporary pointer so you don't lose your head anchor. Rule 2. Check for null before accessing any data so you avoid those nasty segmentation faults. Rule 3. Check the empty list condition immediately to handle any weird edge cases. And Rule 4. Always advance the pointer at the end of the loop so you don't accidentally create an infinite loop. And speaking of loops, let's look at 2 final failure states you should permanently avoid. Mistake 1 creates a frozen infinite loop. Here, the developer printed the data but completely forgot the current equals current dash next advancement line. The pointer never moves, the condition is always true, and the program just freezes forever. Mistake 2 is almost as bad. The developer used while current dash next null for a standard print or count task. Because they checked current dash next, the loop stops one step early and utterly fails to process the final node in the list. So for basic traversal, always use the correct approach. Check current dash null to ensure every node, up to and including the very last one, gets processed. This all builds to our ultimate quick reference. We've got our foolproof traversal template, our core rules, and our summary definitions, locking in concepts like counting, printing, and pointer advancement. And critically, take a note of the complexity here. Because we visit each node exactly once without storing any new copies of the list, this highly efficient algorithm runs in time O of n and space O of 1. So you now have a really solid grasp on forward-linked list traversal in C. You know how to access data, protect memory, and operate efficiently. But I want to leave you with a question to chew on. In this structure, the conga line only moves in one direction. What happens when your application demands that you traverse moving backward? I highly encourage you to explore the fascinating world of doubly linked lists next, where every single node holds a pointer not just to the future, but to the past. Thank you for joining me on this explainer, and keep coding.